entitled The Limit of Present Methods, Future Perspective Particle Filters, where my lecture actually will be a number of various comments on, in particular, ensemble assimilation and particle filters, but other things too. So it's more, it will not be a very structured presentation, just a number of well, already start. It has been said repeatedly that algorithms, the blue, which can be implemented in at least the forms of Kalman filter, Kalman smoother, variational assimilation, in the exact linear and Gaussian case, achieve Bayesian estimation, which can be considered being the ultimate purpose of assimilation, define the conditional probability distribution of a state of a system, condition to all the available relevant information. Of course, stated in these terms, statement makes sense only if all the available relevant information can be described in terms of probability distribution, which may not be absolutely obvious. Okay, but so are there algorithms which can produce exact Bayesian, can lead to exact Bayesian estimation beyond the strictly linear and Gaussian case? Okay, there is an approach, particle filter, which is meant to do that. I already stress that among the methods which have been presented by Pavel and I, variational assimilation is difficult to say where it really originated from, because people have been doing optimization for estimation almost since computers have been available. But it is true that variational assimilation was developed specifically in the context of assimilation of meteorological and oceanographical observations, with little contact with the outside world, except for the use of the minimization algorithm. From the very start, people who did variational assimilation for meteorology or oceanography use minimization algorithm of the type of conjugate gradient or quasi-Newton, which they borrowed from specialists of minimization. They interacted with those specialists, but never went very far by themselves into those minimization techniques. Ensemble Kalman filter was a creation of the world of geophysics, which is Geir Imensen, who in the year 1994 suggested, Pavel maybe can tell me, so 1994 suggested ensemble Kalman filter, and this did not exist elsewhere, and it has caught up elsewhere. There are people now outside the fields of oceanography and meteorology who use ensemble Kalman filter. In fact, it has become a field, it has become a topic of study by applied mathematicians in its own right. Did originate in oceanography. Particle filter, but on the contrary, originated from people who had no particular interest in meteorology and oceanography, but did that for small, strongly nonlinear systems with small dimension, but it originated for elsewhere. For instance, among the name of the people who did particle filter, there is a man, a Frenchman by the name of Doucet, who wrote a book on what is particle filters. I think it was published in 2001, but before people in meteorology and oceanography really became interested in those techniques. Well, the principle of particle filters is actually very simple. What the system produces is an ensemble at a given time. An ensemble is an ensemble of points in state space, just like ensemble Kalman filter. An ensemble. So these are denoted x. Again, x is the same vector. X, n is the index which identifies the elements in the ensemble. There are small n identified elements. There are capital N of them. And these background is again used background because it is an ensemble which comes from the past. The description that we have here is again essentially sequential. And each element has its own weight. It's a probability, which is P of x b n. So element n has weight P of x b. And then an observation vector becomes available at that time. And once one to use, what is the probability that x equals x b n given y? And what's the Bayes rule? Is everybody familiar with Bayes rule? No point. And that is proportional to the probability of x b n, which comes with the particle, times the probability that y equal x, that the observation is equal to y given x b n. And proportionality requires a normalization factor, but the normalization factor is simply 1 over the summation of all of these over n. So it's 3. And so one will establish probability. And if, for instance, y is our form, y equal hx plus epsilon, and epsilon is uncorrelated with everything else, y will be equal to x n. If epsilon is equal to mod y minus x n, and so this probability, and if epsilon is uncorrelated with anything else, this probability here is simply the probability that epsilon equals y minus x n. So it's easy to compute if epsilon is correlated with anything else. If epsilon is assumed to be correlated with the probability distribution of the SDN, the expression is much more complicated. And so this defines a way of updating weights. If the observation, if there is uncorrelation, this defines a way of updating weights. So we carry the ensemble, each element having its own weight. The idea is very simple. Okay, in this approach, the particles are not modified at the time when it did. Each particle comes and is not modified. What is modified is the weight of the particles. And this asymptotic converge for asymptotically in the sense of large ensembles to the Bayesian probability distribution. And as clear seen, if the error epsilon is supposed to be uncorrelated with everything else before, it's very easy to infect. Now so it has all kinds of virtues. What happens in practice? This is the results of simple experiments made by Chris Snyder at NCAR. NCAR, for those who don't know, is the National Center for Atmospheric Research. It's a research center, research federal center, NCAR, National Center for Atmospheric Research, which is located at Boulder, Colorado. You know what place? Boulder, city in Colorado, located at the foot of the Rocky Mountains, at a place where there's flat plains and the mountain begins. I mean, people have the mountain at the back of a garden, and there is a small hill there, on top of which there is a building which houses NCAR, and this building is an architectural curiosity. It was built by the Chinese architect, but now I think he's become American P, and it is one, it was well known, and it is an architectural curiosity. It was used for shooting various films, in particular one film by Woody Allen, which is called Sleepers. It was a scene of Sleepers, but it was shot partly in Edgar. So, there is an implicit and important research group. It's not a university group. I mean, it does lend to universities, in particular, the local university, but it's not a university group. And so, let me remind how it is read. Okay, he looks at the weight, which is in W high, and he looks at the statistical distribution of the maximum of the weight. So, he has the statistics are obtained over 1,000 independent realization of the, 1,000 independent realization. What was, I don't even remember how it came back, let me think. So this is the histogram of the maximum of the weight. Here there are, yes, 1,000 NE is the size of the ensemble. NE is the size of the ensemble. Ensemble 1,000. It was a very simple system. Very simple system. The dynamics were absolutely precise. But the dimension of the system was 10, 30, or 100. So that makes, for instance, in the ensemble there were 1,000 elements, each of which consisting of 10, 20, 30, of 100 coordinates. 10 here, 30 here, 130 here. And the dynamics was present. And this shows the distribution of the maximum, statistical of the maximum of the weights after the filter had been implemented in the various time steps among the 1,000 realization. So we will see that in dimension 10. The maximum value of the weight, which is found most often, is about only 1/10. Within 30, the maximum of the weight is much flatter, the distribution is flatter. And in dimension n equals 100, the maximum of the weight is almost equal to 1. And so if the weights add up to 1, this means that in those situations there is one particle out of the 100, out of the 1,000. There was one particle which has all the weights, all the other particles have been negligible weights. The weight concentrates on one particle. And for one time on, of course, everything is lost. But that particle will be the only one which retains the weight, and which, unless observations seem to happen to be, an observation happen to be extraordinarily close to one of these particles with small weights, what will happen is that one particle concentrates on all the weights. All the weights. Of course, that's not what you want. You want a real sample. So in large dimension, the symbol scheme for particle filter that I have described as the result as concentrate the weight in eventually one particle. And so that in addition, that's the average squared error of the posterior mean, what looks at the mean of the ensemble, looks at the distance between that mean and reality is produced behind, and looks at the difference. Here at 5.5, 25, 127. So not only the weight concentrated on one particle, but the particle is very bad. So, and Snyder came to the conclusion that in order to maintain balance, to maintain something which is meaningful, the size of the ensemble has to grow exponentially with the dimension of the system. Again, I said that particle filters were first developed for systems with very small dimensions. So that doesn't seem very encouraging. Actually, many developments have taken place, and many developments have taken place which I'm not fully aware of. For instance, recently, at the beginning of this month, the meeting of the European Geophysical Union in Vienna, two presentations were made by Peter van Leeuwen and Robert Muller, both persons who study particle filters, on what they call the implicit particle filter. And what you can say, I've not had the time to fully study what they do, and I will not be able to describe what is implicit particle filter, but both say it's promising. The way to solve the difficulties. Well, the problem originates in what is called the curse of dimensionality. What people call curse of dimensionality is that in large dimension, probability distribution are very diffuse, so that in practice, very few this quantity here, which is called likelihood of particle n, is likely to be very small, actually for all particles. There will be one which will have a larger likelihood, and that one will contain much of the weight. If it's high, everything is Think then, the curse of likelihood in the way can be said that it's relatively easy to have intuitive perception of what a probability distribution is in small dimensions. It's much more difficult in large dimensions. The intuition one can gain about probability in small dimensions may be deceiving in large dimensions. Okay. And so Benson and Snyder evaluate the stability of filter requires the size of ensemble to increase exponentially with the split dimension. So there are alternative possibilities, which I will not describe in detail. I don't know them well. I mentioned that they exist. And the relatively good review of that is a paper which was written precisely by Peter van Leeuwen in an article published in the Monthly Review at the end of October 2009. Particle filtering in geophysical systems. And since 2 years ago, well, hardly more than 2 years, a year and a half ago, the situation has evolved. Something that I will not be able to give you an up-to-date description of the situation. So, well, you know what I said, the particles are not modified. The weights assigned to each particles are modified, not the particle. Of course, one thing which can be done is to redefine new particles. So, the simplest way to do that, draw a new ensemble according to probability distribution defined by the updated weights. You have new weights, and you draw a new ensemble among the same particles, but with the probability assigned by the weights. So that if one particle has weight 1/2, half of the particles you draw will be identical with that particle, and so on. So you draw a new ensemble. Then give the same weight to all particles. Particles are not modified, but particles with low weights are likely to be eliminated, while particles with large weights are likely to be drawn repeatedly on surface. For multiple particles, add noise, I'm going somewhere from the start, in the form of model noise, then temporal integration. If there is model noise, then particles that are identical at the time you do the update will then diverge in the ensuing integration if you add to them random independent random marks. Of course, here there are many possibilities as to how add the noise. Well, the random character of a sampling introduces noise. So alternatives exist, such as residual sampling. Updated weights are multiplied by ensemble dimension n, while and p copies of each particle n and taken, where p is the integral part of n, w, n. Okay. And it's the way to avoid noise, which is present in the random sampling that is there. All these things improve the situation, but not very much. And so another technique which I mentioned, that I must say I don't fully understand it. So if you have questions about it, I'm afraid I won't be able to answer precisely. Is what is called important sampling. Use a proposal density that is closer to the new observations than the density defined by predicted particles. For instance, the density defined by an ENKF, which can be run in parallel or in advance. And then you do in fact something which may be described as cheating. We define a new probability density, which you assume is likely to be closer to the real probability density you are looking for, and you use this new probability density as a first estimate. For instance, you run an ensemble Kalman filter up to analysis line, will define the density, and you use this new density as a kind of first density somewhere. There are several ways to do it, but you anticipate, instead of just taking only the probability density defined by a cloud of particle, you anticipate on what the density you look for is, must be. And there are various ways of doing that, and I would say I don't fully understand, I don't fully know how they do. And for instance, there is a guided sequential importance sampling, which actually was already studied by Peter and Lehman as long ago as 2002. And the idea is to do the observation at time k to ensemble of atom time step anterior to k, or to nudge the integration between time k plus 1 and k towards observation at time k. So you anticipate. I don't fully understand. It seems like cheating in a sense, but of course, if it can prove the thing, it's all right. It also seems to have the consequence that the independence in the various particles is to some extent lost. So I don't fully understand how all this works, but I know it exists. And this is an example of the results performed by the results of experiments performed precisely by Peter and Lewin. This is the comparison of the RMS error between some quantity which is expressed in meters square per second, so the geopotential, between ensemble mean and independent observation and the standard deviation of the ensemble mean. Yes. You have an ensemble, and you want to assess the quality of that ensemble. One thing to do, of course, is to look the mean of the ensemble and to compare to observation. Yes, you have an ensemble, and you have an observation, and you want to compare the quality of it. You want to assess objectively the quality of the ensemble. Of course, but such an assessment can only be statistical. Yeah, right. But at the end of time, I will say a few words about it. Let us suppose the following situation. You predict a probability distribution, which I represent as being continuous. That's a probability distribution you predicted for some variable. Now you have a very fine observation. is here. Is it good? Is it bad? Impossible to tell. As long as it falls within the range of a predicted probability distribution, as long as it's not 10 standard deviation or 20 standard deviation away from the mean of the probability distribution, it's neither good nor bad. It's within the predicted limits. And so what? You might say that if the observation falls here, right in the mode of the probability distribution, yeah, yes, that's good. No, it's not good, because if it as well falls here, what it means that you should not have predicted that, because if you predict that the quantity you're interested in must be below this threshold by, let us say, probability 10%, and it never falls, and the observation never falls in that lower decile, then that's wrong. You predicted too broad a range. That's wrong. So, if the observation falls there just in the mode, close to the mode of the expectation of a predicted probability distribution, isn't bad. But if it is always happen, it is bad. So the only way to check something like that is to wait until the particular probability distribution has been predicted a number of times, but with the time, and to check how the observations are distributed with respect to the prediction you've made. So if you find then that when you predict this particular probability distribution, the observed reality is distributed something like that, well, okay, there is a good agreement to say the prediction of that right probability distribution is statistically correct. But if you find that when you predict the right probability distribution, the reality is distributed according to that, something like that, then it's wrong, obviously. Because when you predict this probability distribution, the statistical distribution of the reality is like that, which obviously is totally different. So this is to stress that the assessment of the quality of a prediction of an ensemble, the assessment of the quality of prediction of probability distribution can only be statistical. Except some extreme cases, it can only be statistical. It means nothing to say that a particular ensemble prediction is right or wrong. It can only be statistical. As long as the reality falls within the range of uncertainty that you have predicted, you cannot say anything on one individual realization. And of course, that is why many people, in the general public and elsewhere, laugh when we are told that meteorologists make probability forecast. What does that mean? If they predict 40% of probability for rain, well, it rains, okay? I predicted 40% probability, so if it doesn't rain, well, I predicted 60% probability for no rain, so that's good. So they will also always get away safe. So many people say for probabilistic over prediction, it's just nothing. You cannot say whether one individual probabilistic prediction is right or wrong. The assessment cannot be statistical. And of course, this extends to any form of probabilistic estimation, including ensemble assimilation. If you want to assess ensemble assimilation, the assessment can be only statistical. You cannot say. When you do a deterministic forecast, that is, you commit yourself on one particular value, it will rain or it will not rain. It's either of the two, of course. Then you can be wrong or you can be wrong or right on one end. But when you allow for the margin of uncertainty, it's not possible. We only see two cases in which it is possible to say, I think, that a probabilistic prediction is either wrong or bad. The first one is the case when you predict this, something very much P, and you observe that well beyond the range of the uncertainty that you're predicting. So here I'm going to say that's wrong. And the case when you can say it's good, do that again. This, something so predict something which is very sharp in comparison to what you do usually. You predict temperature tomorrow for tomorrow with an uncertainty of a margin of a fraction of a degree Celsius. And then, well, the range of your prediction of the uncertainty is unusually small, much smaller than the usual error in the forecast. And you find that, yes, the observation falls within that very narrow range of uncertainty. Then you can claim, yes, my probabilistic forecast was good. Good because of a conjunction of two reasons. The predicted range of uncertainty was exceptionally small, and the observation has fallen in that very small, exceptionally small range of uncertainty. But I think these are only the two reasons in which one can reasonably say that one individual probabilistic forecast was either wrong or good. In ordinary situation, you cannot say anything on what individual probabilistic forecast. So among the many scores, and it's a question which I know well, which I've studied quite a bit personally, among the many scores that can be considered for assessing the quality of probabilistic estimation, whether that is assimilation or prediction, one is the following. You predict a probability distribution for some quantity with a standard deviation sigma. Now, I take the mean with probability with expectation m and standard deviation sigma. This is what you predict, probability distribution, which most often will be in meteorological application, will be in the format of an unstable of points. Finite sample. And then there is a very fine observation, x, O for observation. I take the difference, x, O minus m, and I divide this by sigma. If, with that particular probability distribution, I predict that particular probability distribution a large number of times. If the observed value xo are distributed according to that probability distribution, then by very definition of what mean is and expectation is and standard deviation is, this quantity must have taken over a large number of prediction of that particular probability distribution with expectation m and standard deviation sigma, must have expectation 0 and variance 1 by the very definition of what an expectation and variance is. So you can do that. And actually, since the values must be the same for all probability distribution you may predict, because you include here the mean, the expectation, and the standard deviation, you can mix together all the probability distribution you predict and compute this ratio for every realization of a process, independently of which particular probability distribution you predicted. And then you check whether this has expectation 0 and standard and variance 1. And if it is, then it means that your system is correct. In that, it doesn't mean that it's correct, but no. But if you find either something which is either different from 0 or different from 1, then it means your system is not correct. But if you find that 0 and 1, then at least there is consistency. Usually, like a question of consistency I discussed in the previous lecture about consistency between the a priori specified and the a posteriori observed statistics of innovation. So actually, Peter Van Leeuwen did that in slightly different terms, but in this case, he plotted what was then as a function of time, comparison of Hermes error between ensemble mean and independent observation, dotted line. That is actually big. Hermes error between ensemble mean and independent observation. That is actually the numerator here. And the standard deviation in the ensemble by the denominator. And he finds that these two are rather close, and actually over time oscillate in the same way, which seems that his particle filter has correctly predicted, correctly. This is one can expect from a correct prediction of the uncertainty.
Yes. The particle filters are supposed to handle nonlinearity and non-determinacy. Those develop for larger cycles. But what we see here is very small cycle, one day.
Well, it was oceanography.
Yes.
And what you say, well, particle filter are supposed to, yes, handle nonlinearity in the sense that the temporal evolution follows nonlinear equations, just like in the subatomic filter. The updating process is different from the one in subatomic. So, repeat again your question?
No, but my point is that if this, for example, model was some sort of standard oceanographic model of some kind, then the tested regime was not that in which you would like to test your particle filter as such, because perhaps ensemble Kalman filter would work even better in this particular situation, because it looks very linear.
Okay. For what I know, Peter Van Leeuwen did not compare with ensemble Kalman filter. It might be interesting. Yeah, absolutely. It might be interesting. Absolutely. I don't claim that. No. I don't think you made a comparison. Yes, of course. Well, what all I say about particle filter? But not very much. What I can tell you is that active research is performed in particle filter by, among others, Peter Van Leeuwen himself. I mentioned the name of Robert Miller, who is at Oregon State University in Oregon, northwestern US. And also there is a man, Alexander Schoen, who is not particularly good with many things which have nothing to do with the atmosphere of the ocean, but is also working on these questions. And in particular, they are presently working on what they call implicit particle filter. I don't know what exactly was filter implicit, but they claim that the problem of the curse of dimensionality and the general problem of collapse of ensembles of particle filters in large dimensions is going to be solved. And so these filters have the property that they don't rely on any particular assumption as far as concerns the probability distributions to be looked for. It is not a priori valid for any probability distribution and not particularly for Gaussian probability distributions. He wants some more on this aspect, and I'm going to make some other. Well, is the ensemble approach can it be extended to variational assimilation? Can I be extended to Kalman filter, as explained to us, and also particle filter, as I've described it, and as I think they exist now are still sequential. In particular, if, just as in what I said yesterday, if there is correlation, well, correlation is no more appropriate because there is nothing linear in the system, but if there is statistical independence between new observations and older observations, or in the model or in the model error, then although of course Bayesian estimation is in principle is feasible in principle, we find again another problem. But if one uses the piece information and then ignores it, and new information comes up which is correlated, which is non-independent, not correlated. I'm speaking of probability distribution, not linear, which is not independent of the data. Then there is a difficulty which I mentioned yesterday, but you cannot be optimal about it. You cannot be fully Bayesian if you ignore it. So I don't know what particle filters can do or cannot do in this respect, except again, but the only solution is to extend the state vector to augment it to the time dimension. Obviously, the only solution to solve the difficulty. But can the ensemble approach be extended to variational assimilation? And to answer my question, I write again. Yes, no. Yes, I have it here, so I can go there. To go back to what I said in my previous lecture. So I consider again this problem. And an x, zeta z, z equal gamma of x plus zeta. Gamma is a known matrix of coefficients. Zeta is an unknown error, but with statistics are supposed to be first and second order moments. And I do least square estimation and biased least variance estimations of that. And I find the solution is it's not to react. What is the solution? It's a gamma transpose is one thing. Gamma transpose is one. Z minus mu. Mu is the application. Covariance matrix associated error is equal to gamma transpose. That is the factor here. And I said that if the error is Gaussian, these equations, which are here, now solve Bayesian estimation in the sense that the probability distribution over x given z is the Gaussian probability distribution with expectation xa and covariance matrix PA. So now, this gives actually a ready recipe for obtaining, in the case of linearity and Gaussian error, a Bayesian sample. What do? I just perturb the data with its own error. So zeta, z, equal, transform it. So z plus delta, where delta is a realization of the error of the error of zeta d. And I do the analysis on that. So I obtain gamma transpose, gamma S1, gamma transpose, S-1, S minus mu, Z minus mu, plus the same quantity, which are respectively, which I write correctly, gamma transpose, S minus 1, delta. Because I've perturbed the data by a delta by the delta. So this is linear. So this is XA. So when I vary delta, I obtain XA plus something which I call gamma. Well, gamma is this. Gamma, of course, has expectation 0 because, well, I must assert the data with the unbiased error. But, I put the bias in there. And what is the covariance of gamma? Well, it's gamma transpose S minus gamma transpose S minus 1 delta time the transpose of the same thing, that is time delta transpose, time S minus transpose, which is S minus 1 because S is symmetric, times gamma, time the transpose of that, but that is symmetric, so the transpose of that is the same thing. Minus. And now I take the expectation of that. That is the variance of the delta. I do n analysis, n variational assimilation. And I do take the expectation of that. All that is non-random. That is non-random. This is the only random component. And what is the expectation of that? Is S, precisely because delta has been taken as the realization of the error on the data vector. So here I have S. So S1, S minus 1 and S cancel out. S minus 1 and S cancel out. It remains gamma transpose S minus 1 gamma, which cancel out with that. It remains S minus 1, yes. It remains gamma transpose S minus 1 gamma, which cancels up to here with that. It remains gamma transpose S minus 1 gamma minus 1. And that is precisely the covariance matrix of the Gaussian probability distribution, the conditional Gaussian probability distribution. So I have already a recipe for doing ensemble variational assimilation. I perturb the data according to their own error law. The data consists of the background, the observations, and if I do weak constraint variational assimilation, the model itself. I perturb the data according to their own probability distribution, of their own error probability distribution. For each set of perturbed data, I do a variational assimilation. I obtain n model trajectories of n sequences of state over the assimilation period. In the linear and Gaussian case, these n trajectories are n sequences of model states over the assimilation period are a sample, make up a sample of a conditional probability distribution. So I have got a ready recipe, which may numerically be costly, to do ensemble variational assimilation, which in the linear and Gaussian case will lead to a Bayesian sample. That is done. What I've described is described, to my knowledge, done now in 2 places. In Météo France, they do that in the assimilation phase, but actually not so much for doing fully ensemble assimilation, but for being able to carry out, to obtain the background estimate for the beginning of an assimilation window, for the beginning of new assimilation window. This is an assimilation window, typically 6 or 12 hours. I told you that in variational assimilation at present, the background error covariance matrix is taken independently of the situation, climatological, which of course is a weakness of the system. What they do at Météo France is running a few variational assimilation according to what I have said, maybe at a reduced resolution, to obtain here a number of points which will be used in the definition of the background error covariance matrix for the next assimilation cycle. Maybe you've used with another information, but this is what they do, and obviously this is the first step towards full ensemble variational assimilation. This is also done at ECMWF, but not fully for the analysis for the high resolution forecast, but for defining the initial condition of the ensemble forecast. Because as I told you, they have a high resolution deterministic forecast. Maybe I didn't tell you, I didn't tell you that in the present ECMWF system, there is a high resolution T equal 1200 or 1400 deterministic forecast, and 50, and twice a day, a 50 ensemble prediction performed at lower resolution. Of course, the question is how to define the initial condition for the ensemble prediction. And now they use partly things like that. They do variational assimilation, so they obtain points at the starting time of forecast, which are used not for starting the high resolution forecast, but for starting the ensemble forecast. Okay, so this achieves Bayesian estimation in the linear and Gaussian case. Of course, reality in our case is neither linear nor Gaussian. So the question is, what do we lose, if anything, in terms of Bayesianity, if we apply that recipe? That's very easy to apply, it's only a matter of completion and cost. If we apply that recipe in a nonlinear and or non-Gaussian case. And actually, right now, I am working on this aspect, a small nonlinear model. And more or less nonlinearity, and we have more or less non-Gaussianity, and we do experiments to assess the quality of analysis according to the type of criterion I described 10 minutes ago. That is, in terms of statistical performance, not only in terms of individual performance, because again, an ensemble estimate cannot in general be evaluated. The quality of an ensemble estimate, of an individual ensemble estimate, cannot in general be objectively assessed. So, this is a development which is being done, which is ensemble variational assimilation. Okay. Now we come back. Part 6. Yes. Now a few additional comments on assimilation. So, Pavel and I have spoken of variational ensemble Kalman filter and variational assimilation. I've said a few words of particle filters and of ensemble variational assimilation, which is being developed. After all, what are the compared quality of the two approach, ensemble Kalman filter and variational assimilation? I say again, but in the linear case, both algorithms lead to the same result. But in reality, well, everything is not linear. What is the performance? It's difficult to make comparison, real size comparison. This model is so big and a clean comparison. There is one place where this can be done. It is the Canadian Meteorological Center, which has taken the trouble of developing both a variational system for variational assimilation and for a system for ensemble Kalman, right? Ensemble Kalman filter. And Mark Brunner, has made a clean, as clean as possible, comparison between the two. And he finds that for the same computational cost, the differences in performance between the two methods are very small. They exist, but the system are not strictly equivalent because the model used is not linear. So they exist, the difference of this. But some features are to the advantage of the Kalman feature, other to the advantage of the variational assimilation, and the difference of the whole he finds are negligible. Actually, in the sense, It is not so much, according to the results, not so much the method that is used, but the amount of resources that is used makes really makes a difference. Okay. So now I give a number of pros and cons for the two approaches. I say a number of pros and cons. Conclusion of sequential assimilation. You, particular problem, make comments at this stage. To me, the pros sequential assimilation. Conclusion and pros and cons. Pros. It is in a sense natural and very well adapted to many practice situation. In particular, it is well adapted to the situation when new data come in permanently and you just update the latest estimate. And it provides, at least relatively easily, an explicit estimate of the estimation error, especially in ensemble form, because the final output of the system is an ensemble, which by definition provides an estimate of uncertainty. Or variational assimilation, it is in its crudest form, doesn't do that. It produces one state. Of course, ensemble variational assimilation at, of course, a higher cost will produce an estimate. In its raw form, it doesn't do that. And when I said the comparison which has been made by Mark Brunner is about variational assimilation, the unique variational assimilation, and an ensemble filter tuned in such a way as to have the same numerical cost. So ensemble assimilation, which are described here, will of course significantly increase the cost. Well, cons carries information only for one in time. Two remarks. First of all, this is of no real importance if one is interested only in doing a forecast, because when you start a forecast, well, by definition, you can have used only observations performed at the latest at the time when you start the forecast. So the fact that the information is carried only toward the future does not matter anymore at the time you start the forecast, obviously. But when you want to do reanalysis of past observations, then it matters. But of course, as Pavel said, there is also Kalman smoother, which does carry information backward in time. And in prement form, so maybe that's no more absolutely true, because in fact, optimality is possible only if errors are independent in time. So may that not be true, because, for instance, Emmanuel Combe, I said yesterday, told me, he knows well the various forms of ensemble Kalman filter, and maybe Pavel may wish to comment on this one, told me that some form of ensemble Kalman smoother, or maybe filter, are able to take into account observation errors that are correlated in time. But in any case, that can be obtained again only by augmenting to the time dimension the state vector in order to be able to treat several times at the same time in the process. Okay, so the same for variational assimilation. Pros carries information for forward and backward in time by essence, and it is built on the possibilities. It is there from the start. Important for assimilation. Can easily, maybe I should have put relatively easily take into account temporal statistical dependence. And again, this has been done by Heikki Järvinen. Does not require explicit computation of temporal evolution of the estimation error. Of course, this is one side or one aspect, which is that then there is no explicit estimation. There is a gain in computing at this stage, but of course the final product, and if we may want with variational assimilation to obtain that estimate, but that will be costly. And it is very well adapted to some specific problem. For instance, if you want to identify the source of a tracer, you have observation of a tracer, but not really assimilate. And you want to identify where it comes from, with variational assimilation is very well adapted from the adjoint information which was backward in time. Well, happens. Well, it does not really provide an estimation of error, so it's to balance out. Or balance out or not. It's still goes in. We see the advantageous feature and the disadvantageous feature are the same fact. Requires development and maintenance of advanced code, but the latter can have advantages. And actually, I think what some of the people who said Kalman, ensemble Kalman feature is the thing to do. This fact, the need for developing, validating, and maintaining an agile code is an important. Well, I did not say it, but what is called the dual approach, which I only very briefly described, seems to be very promising, but is ensemble variation and assimilation possible? Probably yes, one can say yes, because now it exists, but needs further development. And of course it will improve the cost. Okay. So what else? A number of conclusions. The main two classes of algorithm presently exist for operational assimilation of observation in geophysics ensemble. They offer more or less empirical extensions to mildly nonlinear and non-Gaussian situations of algorithm with the chip-based estimation. Okay. The two classes of algorithm for the useful and for the same cost comparable quality of results. They are far from optimality as a microsheet, as we have more example. There is no obvious way for improving event, but ensemble method meant to produce a sample of a sought-for condition of probability seem most promising. Fully Bayesian of particle filter as the subject of active research. Yes, I'm personally totally convinced that the way in the future in this kind of application is Bayesian approach. That is to produce a description of a condition of probability distribution. And the only way I know for describing a probability distribution in the very large dimension systems that we have, and in which there is no obvious form for probability distribution, it is not a particular analytical form, it is not Gaussian, it is not what uniform it is through an ensemble. So, to me, both for assimilation and for prediction, the way of the future is ensemble estimation. What else? Conclusions. Okay, that's propaganda. But assimilation, which originated from the need of defining initial condition for the forecast, has progressively extended to many diverse applications, a number of applications. So maybe it could be updated. For instance, planetary atmospheres. Now people assimilate observations of the atmosphere of Mars, and it works very well. There are almost, I don't know if it's really operational, but there are now satellites which orbit Mars, making permanent measurements of the infrared radiation, obtaining permanent definition of the structure, of the thermal structure of the atmosphere. This is introduced in models of the Martian circulation. These models work very well. And so you have now, well, I think it would be possible now to produce weather forecasts on Mars if really wanted to. It could be possible to produce daily weather forecasts on Mars. Well, reassimilation of past observations, of course, and that's becoming more and more important. A priori evaluation of anticipated new instruments. You plan to launch a new instrument, some satellite, and you form something, laser, which will measure the wind, for instance. It's, the wind, of course, in the radial direction. It's Doppler effect, a laser which will measure wind by Doppler effect. You want to know how much this is likely to improve the quality of meteorological forecasts. Well, one simple way to do is to put such a laser, satellite-borne laser in a model to make it simulate observations of the run of the model, and then to assimilate the data and to make a forecast and to see how the presence of a virtual instrument improves, or doesn't improve, the quality of the forecast. and all kinds of things. Atmospheric chemistry, oceanic ground, glaciology, magnetism, of course, using the right, I said, both planetary and solar magnetism. There are many domains of application in which these methods have extended. Well, assimilation is related to all kinds of investigation theory, probability theory, instrumental physics, optimization, control theory, computer science, the kind of propaganda. And to finish, a few of the remaining problems, just to say a few. Observability. The problem of observability is we want to know the state of the flow at a given time. What is sufficient to observe? What is necessarily sufficient to observe? We have a satellite which observes today. What can we obtain from a given observing system? But not of the satellite. It's very difficult. In a linear system, it's very easy. In a linear system, you have a linear relationship, and it's only a matter of a rank of the matrix which links the observation to the data you want, and the matrix must be of maximum rank, or full rank for observability. In a non-linear system, it becomes much more complicated. Just to give an illustration of how this problem is. In a linear system, in which, like the one z equals gamma x plus z plus beta, if gamma is independent of the state x, as I assume, well, the problem is just to have matrix gamma full rank, and if a gamma matrix gamma is a full rank, well, you totally observe the observation z equals gamma x over beta. I don't write it. If the matrix gamma full rank, the rank of gamma is a dimension of n, or x, then there is observability. We observe the vector of the observation vector z, the data vector z, contain information on all components of the system. In a non-linear system, there is no such further condition. I just consider the following problem. We have a fluid which evolves in a very simple way. Each fluid particle keeps its velocity. So d, u of the d, where u is the velocity, and d is the particular derivative taken. So each velocity, each particle keeps its velocity. Of course, if a particle here goes faster than a particle there, after a finite time, this particle will have caught up with both particles, and something strange is going to happen. There will be a shock. This happened, it's a shock. No, shock wave. A shock wave. I'm not speaking about shock wave. I'm not going about shock wave. I suppose that the time period over we consider a system is short enough so that no particle has caught up with another one. And you observe, at one time, I observed this half of the fluid. Sometime later, sometime later, I observe that half. If the fluid is moving this way, well, there are a number of particles which I've observed at the first observation time here, which I will observe again on the other side. So I will have observed all particles, and some particles I will have observed twice. So I will know everything. If, on the contrary, the particle, the fluid is going this way, the particle is going this way, at first time, observe this point has been here, at second time, observe that, but there are particles which are here in second time, which I will not have observed. There is no observability. So whether there is observability or not depends, in the normal system, on the state of the system. The question of observability in our problem, we essentially know nothing. What we know only comes from numerical experimentation, and that's all. And of course, that is substantially complicated by two elements. The data are noisy on one hand, and the system is chaotic. So it's two, in fact, complicate very much this problem of observability. But from a point of view of theory, it underlies assimilation. Second problem, more accurate identification and quantification of the errors affecting data, particularly error affecting the assimilated model. I told you, I think, in my first lecture, but the lifetime of a model, of a version of a model, is much shorter, but the time necessary to accumulate statistically significant information as to its performance, so that the model becomes obsolete and is replaced by a new model before we really know what it is worth. So the problem of estimating model error is a major problem. And one, which I mentioned, a number of people are working on that, is assimilation of images. When you look at the satellite picture, you see structures. You can see, for instance, in the one here. No, you can see it here. You see, for instance, a tropical cyclone. Picture of a tropical cyclone picture of a tropical cyclone on the satellite. On the satellite image. A child who has seen 3 such pictures is capable of telling this is a tropical cyclone, because if it is in low latitude, in tropical latitude, there is at present no automatic algorithm which is capable of saying this is a tropical cyclone, it is located at this position. For the cloud structure, I can infer that the wind velocity of the wind, which is is so and so, and then to put those values in an assimilation algorithm. This cannot be done automatically, and there are many other structures. Fronts can be identified, line of discontinuities, or at least a rapid variation of various fields which exist both in the atmosphere and still more in the ocean. Fronts are visible in some pictures. Vortices in the ocean are visible in the ocean. Or vortices which are visible, maybe not in visible light, but in the infrared. There is no way now, no automatic algorithm which is capable of identifying the vortices and carrying information to the assimilation system. There is a vortices at such and such location with such and such characteristics. And of course, it's a very important question. All the assimilation techniques that we have described are based on individual measurements related from each operator to the states we want to estimate. Of course, I mean, in mutual correlation, the individual measurements may bear on the same quality or same quantity on quantities which are related, and that is said to the system, but the system is not able to identify itself, but the structure of the observation is set to the okay.
This is not entirely true.
This is not entirely true.
Some kinds of observations we assimilate, they come from images.
Yes, okay.
So, say some graded products which we assimilate, they are secondary products which come from basically still like images.
But as a human being, as there been an intervention by a human being works very slowly in this context, or is it entirely automated?
What you're saying is mainly true, because if you look, for example, at image of, say, stellite image of chlorophyll or of sea surface temperature, there is amazing amount of information.
Yeah,
you can see by eye, and you only use small fractions of the data simulation.
Yes.
In this sense, it's very true.
But I mean, I know people are working on that, and so this will come. But that it exists at present in a way that the system is capable of identifying a spatial structure or a temporal structure, or is it that the system sees that here there is more chlorophyll than there? And so this is introduced among the Y in the Y vector. Right. Chlorophyll content large at this point, small at that point. That's not recognizing the structure.
Yes. CLS and France, for example, have automatic procedure which identifies the ice drift vector from images by identifying some structures and following them in time. So this one is
okay. For instance, there might be situation in which there is a gradient. Maybe this is the gradient is about the quantity between 2 points. And in gradient in such circumstance, someone who knows the physics of a system can tell, well, there must be a sharp discontinuity between these two observations. There are strong concentrations, small concentrations, and someone who knows the physics of a system might be able to tell there is somewhere a strong discontinuity. A system like the one I've described, if it doesn't know that there is a strong discontinuity, will automatically smooth out the variation and not put a strong discontinuity which may exist, which may physically exist. But typically, so maybe you say that you now have a system which are capable of doing that, of telling on the basis of the physics of the non-physics of a system, but there must be a strong discontinuity somewhere in between these 2 points. This is typically the problem of assimilation of images, and more precisely of structures, spatial structures or temporal structures or both, which are known to exist from the physics, but which the system in most systems, or at least in meteorology, are incapable of recognizing. If you know there is a tropical cyclone somewhere, you know much more about the wind, temperature, and humidity field than just the particular local measurements you may have, because there is a whole complex structure which has a typical structure on which you can see much more than just the individual measurements you may have. And this problem is one of the problems facing assimilation. It is totally outside Gaussian display assimilation, something else. It is still within the range of Bayesian assimilation, of course, but it is totally outside of the blue. Okay, well, thank you.
Thank you. Yes, other questions? Brian? Yes, please. Yeah. You have one? No. Yes, please.
I've got a point, Oliver. I mean, you mentioned the suboptimality in the columns of variation.
Yes.
In what sense of suboptimality? It's not the for the value optimal.
I said there is something that is not optimal. There?
I think if you move a little forward, you move forward.
The what?
No, still further.
Still further back?
Further ahead.
I'm going backwards here.
No,
You
go.
mean here? These have been only 2 slides of, I mentioned explicitly, advantages or disadvantages of the 2 approaches. Only on those 2 slides. It was a question of optimality.
Yeah, you mentioned sub-optimality. You understand what?
Yeah?
The bottom.
Okay.
Oh, they are far from optimality.
Yeah.
Okay. We are far from optimality because we don't take into account, we are not able to fully take into account, at least certainly not variation and assimilation, full non-linearity in its generality, and do not achieve at present, I think, Bayesian estimation. Yeah, yes, okay. Optimality, of course, it all depends on what you mean by optimality. Maybe Bayesianity would have been a better word here, because what I had in mind when I wrote that was Bayesianity. Yes, because, of course, both Kalman filter and variational assimilation are described as being optimal in some context. So, in that case, in the context, in the linear and Gauss one, linear, even we were speaking of Gaussianity, optimal. The blue in linear context is optimal in a precise sense. So okay. Bayesianity, more precise, more appropriate. But they are far from what we would really want to achieve. Okay, other questions?
I didn't understand, quite understand in the particle method.
The particle method,
What
yes.
do you propagate? I mean, like in some kind of filter, you propagate.
Yes, well, the propagation phase in particle filters and in Kalman ensemble Kalman filter is very similar. There are a number of points in state space, but in model states, which are evolved in time with possibly a random noise meant to represent the error, to represent the effect of the error in the model. One difference, one thing which exists in particle filter, but which I don't think exists in any version of ensemble Kalman filter, but I may be mistaken on this point, is that in particle filters, particles may have different weights. Each one carries its own weight, which may differ. I think that in ensemble Kalman filter, all ensemble elements are equal.
In traditional implementations.
But are there variants of ensemble filter?
There's some new versions which try to sort of,
but the difference between particle filter and ensemble Kalman filter is in the way the ensembles are updated. Well, the difference lies. Okay, other questions?
And in particle filters, the weights are calculated by the closeness to the observation.
The weights, well, the weights are given essentially by the likelihood each particle at a given time, new observations become available. So the weights given to the particle are fundamentally a function of the likelihood of the particle, that is the probability that the observation of the quantity are what they are, given that the state is what it is. If the distance between the particle and the observed value is much larger than the standard deviation of the assumed standard deviation of the observation error, then the likelihood of that particle will be very small. And that's why the system eliminates the particle, because once a particle has a very low weight, it will never recover. And so the problem is to generate new particles, which are more likely, and also now to do what I've qualified cheating in information, but anticipate, use, don't wait until the cloud of particles has reached observation time to look at the observation and to anticipate them in advance. To tell them, I want you to go there. Okay. Another question? That's all.
Yeah, then we should thank Olivier again. Very wonderful series of constructed and constructed lectures. There was, Olivier at least suggested or asked me whether there will be an opportunity to publish
Yes.
lectures or even a requirement for that. There is not really a requirement for that, but there is the possibility,
Yes.
certainly present. The question then to the students is whether how much of an interest there is in, or how much of a need there is actually for having a something like a review type article on that, given that you have already a number of different review articles.
Yes, well,
so
I don't have one which exactly fits what I've presented in those lectures, but I've already written documents which more or less cover a more or less large part of what I've presented.
So what do the students feel about that?
Will documents put files our presentation put another would be sufficient.
Because it's because the reviews are in the literature and quite recently, and this is just other presentation of it, so it's not up to date on the review.
Yes, well, at the same time, for us, it's work to write down into the focus.
Yes. Yes. Yeah, right. So from that point of view, very often we at Knowledge don't have the requirement for proceedings. It's more important to have material written in the reviewed literature, of course, which is more profitable both for the authors and in the end it's also more easily accessible, of course. Actually, what I was thinking of was an article in Physica Scripta, which is a possibility still, or always will be. And it could be something which is building upon existing material, clearly.
Yes.
Would therefore be an extension and an update. Okay, so I think that is something we will continue to discuss and we will then let you know of.
Yes, so there's one more thing. So two people didn't order pizza. So if somebody actually want to order, if I go down and pick up the pizza, please let me know.
So then you will just otherwise then run down.
Yes.
No, I order.
So, okay.